everyone. This lesson is going to be focusing on two primary concepts with logarithms. The first is something known as the change of base rule or the change of base formula. And what we use the change of base rule for is to evaluate a logarithm of a base that is not a base of 10 or a base of e. The calculators that we have, pretty much every calculator that you see, has been programmed with two log buttons that do math as a base of 10 and a base of e, and that's it. So how do we get around that on our calculators if we have something that we need to evaluate the value of the base of, or I'm sorry, if we need to evaluate a logarithm that is not in base 10 or base e, and it will not produce common bases if we try to convert it from logarithmic form into exponential form. So what we see up at the top of the screen is the two basic premises of how we're going to convert it. It doesn't matter whether you use log or natural log. It will work the same either way. So we have a log of base A, and it's being taken to some number, log base A of whatever. Well, base A, let's say it's not 10. Okay, so in this case, we're going to say, well, A is not 10 or E, because if it was a 10 or an E, we wouldn't need to know how to do this. So in order to evaluate it on the calculator, what we will do is we will write it as a ratio, saying log of B over the log of A. And these are base 10, which our calculator will do for us. And of course, the natural log, we could write it as that ratio also, and these are, the base of E. So in writing the logarithm as a ratio, as a log of B over a log of A in base 10 or base E, we will be able to evaluate the logarithm the way we can evaluate it in order to get a value of a number of some kind. So here we have a log base 3 of 5. And what we started with in order to try and evaluate the logarithm of some base is to begin with was we said let's change it from a logarithm to an exponent. So using my little loop method here, I would have said 3 to the x power would be equal to 5, and from there we would say, okay, well, let's get a base for the exponents. We can put exponents equal to each other and solve for x. Now 3 and 5 are prime numbers, so they don't have a base in common. So unfortunately, this method won't work like it has with other examples that we've seen in our curriculum. So instead, if we have log base 3 of 5, what we will do is we will write it as a ratio of log base 10 of 5 over log base 3, or log base 10 of 3, and we don't need to write the base 10, and type that into our calculator, and we will get about 1.4650. We could write out the whole thing, but we have to round it at some point. So this is what the decimal, the numerical equivalent would be of a log base 3 of 5. And that is really all there is to it. Now, I mentioned at the beginning that there's going to be two things we're talking about. Change of base is the first one. The other thing that we're going to be talking about is how we can solve we're going to look at some more log equations, but in this case, we're going to have to take the domains into account to see, do I have solutions that work, or do I have any extraneous solutions? So here we have a logarithm, log base 2 of 1.41421, and I'm sure the decimal probably keeps repeating, but they had to round it at some place. Now here it's saying to approximate the decimal and round it to 9 decimal places. Okay, so that is a little extreme, but we'll go ahead and do it. And then it says to verify the number. That basically means to check it. So if I take my number and whatever we get as a solution, if we check it, does it work? Do they both produce the same thing? So here, what we'll say is to use the change of base rule, we'll say log of the 1.41421 over the log of 2, and you just type that into your calculator. And when you hit enter, okay, so the 9 decimal places will be 0.499999. There are 4 nines, and then 6359. Oh, wow. So I think we could probably just say that's about 0.5. Okay, but so this is kind of what we would be looking for as our solution. Okay, so now it says to verify it. Okay, well, how do I verify that? Well, if we were to say, okay, well, we have log base 2 of 1.4 1421. So now we know it's about equal to 0.5. So we could, do our little loopy thing here and say 2 to the 0.5 power and hit enter on our calculator and say, okay, well, does it equal the 1.41421 number? And it does. So 1.1421. Lots of decimals here. Okay. So moving on. Here we're going to evaluate the same logarithm but for different numbers. This is just a function g that says log base 5 of x, and we're going to evaluate it for some different numbers. So if we say g of our first number is 4, we would say log base 5 of 4. Well, to evaluate that using our change of base rule, we'll say log of 4 in base 10 over log of 5 in base 10, and just type that little happy number into our calculator, and we'll get 0.8614. Now, this one here doesn't say to round it out to 9 decimal places, so I'm arbitrarily kind of picking 4 decimal places as the point at which I'm going to stop. So sometimes a lot of math classes or curriculums or tests that you might take would tell you to round it to 3 decimal places. I am just arbitrarily picking 4 decimal places for no other reason other than we have done that previously in other lessons. So now we have g of 20. Well, that would give me log base 5 of 20. So using my change of base rule, we would get log of 20 over the log of 5, both in base 10. And you could do the natural log too, but I'm going to just keep doing log base 10. So you type that into your calculator, and it happily says, well, that is going to be 1.8614. And finally, the g of 100. So we say g of 100 would be equal to log base 5 of 100. Change your base rule says that would be log of 100 over the log of 5, and that happy number is 2.8614. So all of these numbers are relatively similar to each other as far as the decimal is concerned. It looks like all of the input numbers, the 4, the 20, and the 100, it looks like the 20 and the 100 are some kind of factor of 5. So I said like 4 times 5 to get the 20, and 20 times 5 to get the 100. And so I'm sure that has something to do with the fact that I have a 0, a 1, and a 2 on my answers with the same decimal numbers. So that is essentially the change of base rule, and that will pretty much, for all the things that we've studied so far, now there is absolutely no logarithm that we cannot do. So we started with basic logarithms as far as, well, what is it? How do we evaluate it? And we said, oh, well, we could just convert it into an exponent and see what a common base would be and go from there. And then we saw, well, there's some things that we can just type into our calculator. It's just, because it's a log base 10 or a log base z. And okay, well, we'll just worry about the other bases later. Well, now we've gotten to the later, so any logarithm of any base can be evaluated as a number using this very simple change of base rule. All right, so moving on. Again, the second part of this lesson is going to be talking a little bit more about equations of logarithms. The equations, again, the slightly more complicated ones that we have been practicing will require us to use some of the properties of logarithms that we have been looking at recently, meaning how do I condense a logarithm into a single term so that way I can try and evaluate it and try and solve it. So the logs that we're going to have here, the equations that we're going to have here, they're going to have more than one log expression in the problem. Okay, so the first step here, combine the logs on each side again, so that we're going to compress things. So if we say log plus another log, we combine them through multiplication. If we say log minus another log, we combine them through division. Uh, the equations should have bases that are the same, so once I have a single log expression on both sides of the equation, we no longer need to worry about the logs. Just like with the bases in an exponential equation, we can forget those and just take the expressions, set them equal to themselves, and solve for x. Now, the one thing that we're absolutely going to have to start talking about now is checking for extraneous solutions. So in the process of solving an equation for x, we may have more than one answer for the equation. But because the domains of a log function are going to be from 0 to positive infinity, positive numbers, sometimes those answers that would produce a negative number, we have to check to see, well, will they actually work? And let's take a look at one. So here we have a slightly more complicated logarithm equation, meaning that what we have done in the past with our log equations is, well, we kind of had just like one term that was a log, and then maybe we added a number to it or multiplied a number to it, and we would use our normal order of operations to isolate the logarithm and then solve from there. But here we have three log expressions. Everything in the equation is a log, so we have to use our rules, our properties of logarithms to try and condense them into one log on both sides of the equal sign, so that way we can try and evaluate it. It's very similar to what we did at the beginning with exponential equations. Okay, so here the subtraction operation between the two logs, that says I'm going to write this as a single log, base 3, and the numerator, I'm going to divide these two expressions to each other. So the numerator is the one that was written to the left, the one that was written first. So this is x plus 6 over the x of the second log on the left-hand side, and that's going to be equal to log base 3 of 5. Now, at this point, we have the logs condensed. We have a single log term on the left side and on the right side. So at this point, just like with an exponential equation, once the bases are isolated as a single base here and a single base here, and the bases are the same, we don't worry about them anymore, and we just write whatever is in the parentheses as something equals something else, as a simple equation, and we'll solve for x like normal. So here, get the x out of the denominator by multiplying both sides. So the x's on the left side simplify to be 1, so that gives me x plus 6 is equal to 5x. Move the x from the left side over to the right side, and that gives me 6 is equal to 4 times x, and divide both sides by 4, and 6 over 4 simplifies to be 3 over 2, and that would be the solution. Now, what I would do, first of all, because this is a positive number, I really don't need to check to see, well, is it a good solution or is it an extraneous solution? Because the domain of our logarithms are going to be positive numbers. So if I take the 3 over 2 and I substitute it into the equation, meaning if I put it 3 over 2 here, 3 over 2 here for x, and I say, okay, well, do I get a negative number? No, of course I don't, because I say positive plus positive and positive numbers. So we don't have any negative numbers for our logs. So this is a good solution because it doesn't produce any negative numbers in my logs. Next equation. Here we have logs, again, 3 logs, one on the left side, 2 on the right side, but the base of all of the logs are e. So again, we will take our rules of logarithms and condense the log on the right side of the equal sign. And because these are added to each other, that tells me I'm going to say multiply those two expressions to each other. So I'm going to say the 6 times the x minus 1. And on the left side, that poor log of 3x, he's not doing anything. He's waiting to join the party here. So on the right side, we'll distribute the 6 into the parentheses, and I get 6x minus 6. And now we've condensed the 2 logs from the right side into a single log. So now we have single independent logs on the left side and the right side. So we no longer need to write the logs because they are in the same base. And we can just set the terms inside of the parentheses equal to each other and solve for x like normal. So I will subtract 6x from the right side and move it to the left side, and that will give me a negative 3x being equal to a negative 6. Divide both sides by negative 3, and x will be a positive 2. Again, to check to see will this work, I would take the 2 and substitute it here for x, substitute it here for x, and see inside the parentheses will I get a negative number. And 3 times 2 is positive, 2 minus 1 is positive, so we don't get any negative numbers with our logarithms. So there is our happy answer. Now the next equation, so you've seen 2 that work, so guess what? This one's probably not going to work. Check for extraneous solutions. There's going to be something that doesn't work here. So let's see what we get. Using our rules of logs, okay, on the left side, let's go ahead and combine them because we're adding the 2 logs together. That says multiply the 2 expressions together. So now these are base 10, so we don't need to write the base. So I'm going to say log of x times the x plus 8 will be equal to the log of x plus 18. Okay, distribute the x in the parentheses on the left side. And I'm going to get log of x squared plus 8x to be equal to log of x plus 18. So now we have a single log expression on both sides of the equal sign. They have the same base. So at this point, we don't need to write the logs anymore, and we can just take the expressions inside the parentheses, set them equal to each other, and solve for x. Now this is, on the left side we have an x squared term, and on the right side we have just an x to the first power. So we're going to take everything, move it to the left side, put it in standard form, and on the right side everything cancels out and gives me 0, and on the left side I'm going to get x squared plus 7x minus 18 to be equal to the 0. And I'm going to kind of move over here to the left side where I have a little bit more room. So we have the, let's get rid of that. So we have x squared plus 7x minus 18 is equal to 0. So we're going to factor this guy now. And so the factors of 18 that if I added them together to give me a 7 have to be a 9 and a 2. So I'm going to say x plus a 9 and then x minus 2. So there we go. And solve each expression, solve each factor. So x plus 9, set that equal to 0. And the x minus 2, set that equal to 0. So here I get x to be a negative 9. And here I get x to be a positive 2. So now we're going to check, do they work? So if I put a negative 9 or the 2 here, and I put a negative 9 or a 2 here, and the negative 9 or a 2 here, do any of them give me negative numbers with the logarithms? Well, the 2 plus the 8, the positive number works because everything inside the expressions are positive. So we know that the 2 should work for our logarithms, okay? So the negative 9. Negative 9 plus 8 is negative 1. So I get a negative number from my log in one spot. Negative 9, well, that is not combined with anything, so I get a negative 9 on the second log. And, well, negative 9 plus 18, it'll work for the last one. But if I get a negative number for a log at any point, it means it won't work because it would be outside of the domain of the logarithm. So the minus 9, that's what we would call the extraneous solution, because it is a solution for the quadratic that we wound up getting, but it is not a solution of the original log equation. So the only solution that we have for this problem would be the 2. And last example that we're going to take a look at, again, we're going to condense the terms on the left side. Pardon me, we're multiplying, or we're adding the logs together, so that means we're going to multiply the expressions. So again, these are base 10, so I'm going to say log base 10 of x times the 1 minus x to be equal to log base 10 of x plus 4. And again, we'll multiply the x to the 1 minus x in the parentheses. So that'll give me x minus x squared to be equal to log of x plus 4. Now we've condensed the logs on the left side. We have a single log term on both sides, and they're the same base. So at this point, we no longer need to write the logs. I'm going to just take the terms in the parentheses, set them equal to each other, and I'm going to solve for x. Now, what I'm going to do, because the 2 on the x squared is the largest degree, but it's negative, so I'm going to take the stuff from the left side and move it to the right side. So here on the left side, everything cancels out and gives me 0, and on the right side, I will get x squared, and here the x's cancel out, plus 4. Okay, so again, I'm going to come up here to the left side of the screen where I have a little more room. So I have 0 is equal to x squared plus 4. Okay, well, let's solve this one for x. Because I don't have an x term by itself, like I don't have that middle term that's x, I'm going to move the 4 over through subtraction, and I will get negative 4 is equal to x squared. And I think you can see what's going to happen here. If I take the square root of both sides, I'm going to get x to be equal to the square root of negative 4, which would give me a positive and a negative 2i. Okay, so those are imaginary numbers. So that means there's really no solution for this example. Okay, and that is pretty much it for the lessons that we're going to be talking about today. Again, change of base is a way to evaluate any logarithm regardless of the base. We can just say log of one number over the log of the other number to evaluate it. And using our properties of exponents as methods of condensing logs, we can solve log equations, but we can also identify if I have any extraneous solutions by saying, do my answers give me negative values if I substitute them back into the problem? Because the domains of logarithms are positive numbers, not negative numbers. So again, as you're watching the video, I hope you're taking good notes, and if you have any questions, make sure you bring them to me to address them in class or in tutoring. And thanks for watching. We'll see you guys soon.